I'm Christian Turan, a senior mechanical engineer.
I'm Jessica Cassis, also mechanical engineering.
I'm Jadalise Poveda, and I'm also a mechanical engineer.
I'm Gerson Harad, and I'm a mechanical engineer senior.
I am Ryan Withrow, and I am also a mechanical engineer.
And we're Team Roar Gold.
Hi, my name is Jessica Cassis, and this is Roar Gold. So our senior design project is to create a walking dinosaur. We decided to build a Triceratops because we wanted to design a quadruped. We're trying to combine what people expect from animatronic dinosaurs with what most of them actually do. A lot of current robot dinosaurs are basically statues with a few simple motions, or they just roll around on wheels. They don't really try to mimic real biological motions. So making a four-legged robot walk in a realistic way can be difficult engineering-wise, so it isn't done much, especially by students. Our project tackles that challenge directly by creating a Triceratops that walks more like a real animal that could be used for education and entertainment. Our main goal with this project is to create a lifelike walking Triceratops animatronic that looks smooth and realistic. To do that, we first focused on the mechanical side by designing a body and leg mechanism that can support the robot while it walks. To create these parts, we used 3D printing to be able to rapidly prototype and create these parts. This method also allows us to quickly make adjustments to redefine our design. Then we also built an electrical system with a microcontroller and servos to power and control the robot. On a broader scale, theme parks and museums could use more realistic walking dinosaurs to make their exhibits more immersive and educational. At UCF, this Triceratops could become a reusable platform for students to learn robotics, controls, and mechanical design in a tangible way. It also gives professors and researchers a way to study quadrupedal motion and animatronic design. A walking dinosaur is also a great way to get students K through 12 interested about engineering and STEM. So here is the first iteration of our Triceratops prototype that focused more on leg motion and design. This short video here shows how we originally designed the robots to move. We later strayed from this design though and created a new iteration from scratch, which ended up becoming our final design.
We ended up making 3 main iterations of our body's design, with each one being an evolution and refinement of what came before. The first iteration focused on creating a general shape similar to the physiology of a Triceratops body, and then designed the layout of the interior of the body to fit all of the components we need to put inside, such as the power source and motors. We eventually settled on having 4 shelves on the interior that would hold all our components, as well as the motors. The holes for the motors were originally located on the lower front of the body and the upper back of the body based on the leg designs at the time. Vents were incorporated on the top of the body in order to aid with the interior temperature management of the body to prevent overheating. The second iteration refined the design once we completed our leg designs, which were now all of unified length. As such, the holes in the upper back were brought down to the lower back in order to match this new philosophy. We also separated the body into its separate pieces at the time for when it would be 3D printed, with each half of the body being divided into 4 pieces total, 2 bottom pieces, and 2 upper pieces. We also designed motor holders that would help keep our motors in place and aligned with the holes by being drilled into the body once the motors were drilled into their respective holders. And then this slide showcases the images of the first and second iteration of the body. The first iteration showcases the hole in the back being on the upper shelf, and then the second iteration shows when that hole was moved down to the bottom. The second iteration also shows when we started adding pegs and holes to the robot for when it would be separated into its 4 different pieces. Those holes and pegs would aid in the assembly. And then the lower image showcases the motor holders and how the motor would lay into them, as well as where the screws for the motor would go into the holder, and then where the holder screws would go into the body. The third and final iteration of our body was focused entirely on refinement and optimization of the current design. To start, holes were added to the front and back of the body, as well as pegs in those respective areas to hold the head and tail parts of our dinosaur in order to complete the look of a Triceratops. We also removed the upper shelves from the body as we found out that we had enough space on the lower shelves to contain all of our interior components, so the upper shelves were no longer needed and it would help reduce the overall weight of the robot if we removed them. A single small piece was kept in the back of the body in order to hold the Arduino that would allow us to control the robot and give it commands.
Hello, today I'll be going over the initial leg design for a quadrupedal robot. As you can see here, our leg consists of five main 3D printed parts and 6 purchased parts. We chose to 3D print them for prototyping sakes, cost efficiency, and adjustability. All shafts were toleranced with with clearance of 0.01 relative to the holes. We used a 24 teeth pulley with a 70 teeth belt, and it ended up weighing a total of 250 grams for our first iteration. The next step to see what improvements could be made for the initial leg design is to run an FEA analysis to see the displacement and the stress buildup and possible strain. There's no significant information for strain, there was no critical points for strain areas, but we can see 2 critical spots highlighted by the red color on the simulations, one being stress concentration on the corner of the bottom part of the leg. After doing some research, I concluded that it may just be due to the sharp corner, as sharp corners tend to concentrate stress around that area. That critical stress also kind of leached downwards to the rest of the leg, where we can see there's a pretty pertinent green mark going down the bottom part of the leg. For the displacements, we can also clearly see that there's a lot of displacement, around 7.7 millimeters of displacements near the top, where it is going to be loaded onto the body. And the FEA was ran to simulate a 5 kilogram body weight, which is half of the body weight of the robot. Well, the half of the maximum predicted body weight of the robot, as there's going to be 2 legs in contact splitting that mass on the ground at a time. As we can see, the same simulation was ran with a 5 kilogram weight per leg. The stress concentration was analyzed, and as you can see, there's absolutely no concentration there anymore. It is a completely stable and structurally sound robotic leg, designed to now carry a lot more weight than even the 5 kilograms, so its potential for carrying other objects or transporting things is improved. Slight stress going down the leg is also gone as a result of getting rid of that critical stress buildup on the corner part of the leg, the bottom part of the leg. And underneath the simulation, we can see the stress strain graph, where we see the breaking, essentially the critical stress, or the fracture stress, being around 300,000 megapascals for the filament that we were using for 3D printing. And with those, we see that we get nowhere near close the critical stress values, and so we are very sound to use this leg for our robot. The next step was to choose, well, this was done before the leg design, but we ended up picking 3 different servo motors. We would have rather had 2 different servo motors, but due to availability, we had to get 2 different leg motors. So the front legs will have one type of motor, and the back legs will have another type of motor, mainly being the purple and the gray one. And then in the body, we will have the red 30 kilogram motor. Initial assumptions we made was that the 7.4 volt LiPo battery had a stable potential difference of 7.4 volts, and we estimated the current draw of each motor to be around 0.6 to 0.7 amps per motor. Another important information is that the purple and gray servos have an operating voltage from 5 to 8.4 volts, and the 30 kilogram servos have an operating voltage between 4.8 to 7.4 volts. The plan for the setup is to run all motors in parallel, allowing for even distribution of voltage across each motor. To account for potential current spikes, we picked wires suitable for a steady current draw of around 10 amps, at least to come straight from the batteries. We then, after each branch, reduce the gauge. We added bypass capacitors, as seen in this not very accurately, as we ended up adding another one, a small 0.1 microfarad capacitor to get rid of the high frequency noise. And for the wires, we ended up going with 20, 16, and 14 gauge wires. For the final touches, to make just everything much easier to attach and disattach, we added new wire connectors installed. As you can see, those are the orange wire connectors in the picture to the right. And we ended up changing the location of the bypass capacitors and, like I said before, adding that small 0.1 microfarad capacitor in order to reduce high frequency noise. And this is essentially the final power setup attached to the 7.4 volt lithium-ion battery.
So for this testing plan, we first began with FEA simulation tests in our SolidWorks model, which was seen before. From there, we were also advised to try gate motion tests and a possible strength test. However, our strength test was derailed as designing and printing our setup took much time and ultimately could not be properly performed, as can be seen in the printing times shown in the bottom two photos. As for gate motion testing, we were able to print the small part as seen in the top right photo and test the gate motion with our motor from there. So the photo on the left, top left, is one of our iterations of the testing setup, and the bottom two are iterations of another testing setup for the strength test.
Hi, my name is Gerson Harad, and I am talking about the leg motion. So our main goal for the leg motion is to create small and fast steps to replicate large dinosaur limbs. As we know, the Triceratops is a very big animal, so you kind of wanted to do very small and slow steps, how it acted in its real world. So to this, we first did a kinematic analysis. So we took the measurements of the hip and the leg and created a triangle to see at what point the hip and the leg would need to rotate to cause forward movement. So then once we did that, we went through our motor testing phase. So for the hip motor, we wanted to hit a degrees of about 35 degrees, and this was a bit difficult as our hip motor was continuous. So a continuum motor goes as long as it runs, so it doesn't lock in place like a positional motor. So I had to be creative and find out for how long it runs and at what angle we can get an actual hip rotation of 35 degrees. So that took a lot of testing. Meanwhile, our leg motor was positional, and through our kinematic analysis, we needed 40 degrees. So all I had to do was lock that in place for 40 degrees. And here is a video to show you how our leg moves. So as you can see, it's moving all at once in unison, and all of our legs will have delays in between them, so we can get that forward progress. So regarding our electronics, we have two setups. On the left is our prototyping setup. It's a lot more smaller and a lot more agile as we're using jumper cables and a breadboard. Mainly we did this because it's easier to pinpoint issues. However, but like my teammate Chris said, we eventually ran into current issues as our motors draw too much current and the jumper wires are too thin. So we eventually moved into this AWG setup, which has significantly thicker wires, so we can draw more current and output.
We're focusing on finishing and polishing the current prototype. Longer term, our plan is to add interactive features like sensors and sounds that the dinosaur might be able to detect walls and obstacles, and then giving the robot speakers would make it more lifelike, which would allow the dinosaur to roar. And then once it's more reliable, we thought that the robot would work really well in public places like museums or theme parks, and it could be an educational and fun way for visitors to learn about dinosaurs, and people could interact with it safely and see how robotics and science come together. As for the future, we'd like to build other types of dinosaurs or creatures using the same ideas, or even making larger versions of this project. Each new version would help us learn more about motion, balance, and design. So thank you for watching our presentation.